Hello, I'm Ajay and I'm going to introduce the project and go over the dataset we're using. Plastic tag-on tags and barcodes are currently the primary means of product identification in grocery stores, and they have several problems. Firstly, plastic tags generate significant plastic waste. In many cases, there's manual labor involved with attaching these tags onto products, especially those that are not prepackaged. They also have consumer health implications, especially when they leave glue residue on sensitive items such as fruits and vegetables. Most importantly, they're prone to damage, and with a barcode scanner, even the smallest damage can lead to non-detection and significantly reduce checkout efficiency. Our solution is to use a deep learning-based image processing system that does not require any tags. We propose using the state-of-the-art mask RCNN method, which can segment an image at the pixel level, allowing for not only detecting objects in the scene, but also counting how many instances there are of each object. To train our system, we use the MVTech D2S dataset. D2S is a dataset of high-resolution images taken with a checkout counter-like background. The dataset contains images taken under varied lighting conditions with a variety of rotations of each item. Additionally, the dataset also contains images with multiple products and multiple instances of these products in a single image. An accompanying JSON file describes at a pixel level each object in each image in a format that is similar to MS COCO. Here we show a select few sample images from the dataset. In this image, we show how the dataset annotates a pixel-level Boolean mask onto each object.
Thanks for the introduction and the description of the dataset. Here I will mainly walk through the method. In this paper, we use the mask RCN. Instead of doing image classification and object detection, mask RCN is able to do the pixel-level image segmentation. Based on the research, mask RCN is considered the state-of-art for instant segmentation problems. It's been proven very useful across many industries and domains. Regarding the high-level architectures, it's comprised of several components. First is a backbone model and a region proposal network. It acts as the feature extractor over the entire image. With a region proposal network, it does not scan the actual image, but instead, it scans the feature maps. Second component is the ROI classification and bounding box. It's the same as the faster RCN. Is to output a classification and bounding box for each ROI. The third and most important part is the segmentation mask. In this step, it will output the pixel mask to represent the detected objects. This is a very quick summary of the methods. You can find more information in our poster and paper. Thank you.
Thanks, Yongfeng. This is Jingning, and I'll walk you through the experiment part. As what Professor Andrew told us, we picked our single evaluation matrix to be the mean average precision, evaluated over the IOU range of 50 to 95. In order to test many iterations, we also picked a running time less than 2 seconds per step as satisfying matrix. We ran our baseline model and achieved a mean average precision of 24%. By hyperparameter tuning, we are able to improve the mean average precision to 84%. The strategy we used was coarse-to-fine search. Take learning rate as an example. We sample at log scale using 10 to the power of r from -1 to -6, only trained for a few epochs. Once we narrowed down the range to 0.01 to 0.001, we performed a random search for more epochs, finally got the optimum learning rate of 0.002. Similar approach applies to gradient descent algorithm and weight decay. Some key findings, including image quality and deeper network, will improve the performance of the network. We also experiment transfer learning. We found that if we froze first few layers of the ResNet and retrain the rest of the model, was able to achieve the best result. To prevent overfitting, we monitor loss curve from learning and evaluation closely. Also, to visualize the model, we inspect the feature maps from the ResNet activation layers. There are a few challenges in the training process. By comparing the error rate, we are able to identify the initial data mismatch problem and train the algorithm successfully. With thorough hyperparameter tuning, we are able to improve the algorithm precision by 60%. And thanks for your time.